Yes, today I'm going to speak to you about how to proxy NFC comms. So first off, a bit about me. I studied computer engineering at Tux, so that focuses on hardware and software side, and really enjoyed it. Then did an internship at MWR, enjoyed that even more, and now currently security consultant at MWR Info Security. Also on their mobile team, so I enjoy Android, iOS, and all the new stuff that's coming out. Um, Lately did some Xamarin. It's really interesting. So so I'm going to speak to you about the 4 W's of today. So firstly, the overview that I'm going to give you. Just a brief overview of NFC and basically why I did what I did, and just a brief interview before that, and then why it was necessary, why I had to do this research, and what was created, what spawned out of this research, and the improvements that still needs to be done to this. So yeah, during my talk, I quite enjoy questions, so if you want to just feel free, throw them, we can do them. So I guess most of you have seen this symbol before. It's the newer contactless payment symbol. So basically you just go, you take your card and you tap for something, and then you pay for it immediately without even entering a PIN. So we can see that this is a very convenience-driven payment implementation. So convenient, in fact, that I recently read an article that in the UK they are actually petitioning contactless payments due to the fact that the people can't keep track of all the money they're spending now. We can also see that it's quite a relatively new standard. Even though the first actual contactless payment was done in 1997, the official communication protocol was only ratified in 2008. So that's fairly new in protocol standards. And we can see that this is a new physical communication medium for an already existing communication protocol called EMV. So what is EMV? When I tell my friends and family that are non-technical that I did a bit of research into EMV and everything that surrounds it, they're like, okay, what's electromagnetic something? I don't know. So what it actually is, it stands for Europay, MasterCard, and Visa. So these 3 companies came together in 1994, and they saw that there was really no standard way of doing anything in the cards payments industry. So they came together, they standardized this, they wrote the communication protocols, they started implementing security in this, and yeah, all made the world of the card payment industry just a better place. So later on, we saw some other well-known issues joining the fray. They also started implementing EMV in their products. They wanted to give their clients the standard of security that EMV provided. And then today we see like over 23 card issuers that are part of EMV. So EMV is quite a large product spectrum. Most of us know of it from the POS devices where we use it every day in our bank cards, in the ATMs. So for POS devices, it also is used in the mobile counterparts, the mobile POS devices, and also the newer contactless POS devices. So there are a couple of non-payments places where it's actually also visible. So your SIM cards that you use actually also use EMV. So your SIM cards in your cell phones, and also the smart cards that you use for your digital TV stuff also actually uses EMV as communication. So what is EMV actually? Most of us know, we are developers, we know what a communication protocol is, but for just, if there is somebody, it's just a system of rules that allow 2 entities to communicate with each other. So we can basically compare it to Morse code. So to communicate with Morse code, you can use any medium. So smoke, sound, you can shine light at each other. It does not matter how it was sent, just that the message was sent and the format that the dashes and the dots came through. So just like Morse, EMV doesn't rely on what type of medium it's being sent over. So the contactless research that I did is in essence just the same EMV messages, the same protocol, just over a different physical medium. So therefore, that I saw that some of the vulnerabilities that were found in the actual ICC part of the transactions, the actual chip and pin, might also be present in the contactless counterparts. So we can really see that EMV was designed with security in mind, as the protocol is very, very secure. And it is currently the most complex solution that has been found yet in the history of the payments card industry. So if you just look at that, roughly in the 1950s, you were issued with a plastic card with just the number on it. So people thought you wouldn't be able to clone that because nobody can make their own plastic cards, right? So people started making their own stuff, produced fraud. They then started obfuscating the data on mag stripes. So the mag stripes, people also thought this was the holy grail because nobody really knows how EM works. So yeah, eventually people started figuring out that just by hacking apart an old tape recorder, you were able to like read and write your own mag stripe data. So that was also null and void. So they later on went to microprocessors on the chips, which then EMV then took over in 1994. So we can see that EMV requires an active component. So that is what that little chip is on the card. It's actually a little small computer using EMV as the communication protocol. And it's got different applications on it. So applications like either your DSTV decoder or your, say you've got a card, it's your either your credit card or your debit card application. So the thing that makes this chip and pin actually secure is the fact that it stores transaction data internally in an encrypted format. And it also generates a unique cryptogram with every transaction. So that just adds a bit of randomness to every transaction that you're doing. So moving on. When thinking about the actual EMV chips and to attack it, there's two ways to attack it. So you can either attack it on a hardware layer or you can attack it on a software layer. So to attack the EMV chip on a hardware layer would involve you to physically decap the chip. So this is some form of reverse engineering where you rip apart the chip and hope you don't hit the tampering, like anti-tampering stuff. So this is a very specialized process, and if you want to do it properly, sometimes you even require very hectic microscopes and stuff to do it. So it requires you to know what you're doing, and very few people in the world actually know how to do this right. So direct attacks on this is very costly and hard to implement. So it didn't really seem like a feasible attack path to us in the beginning. So it's much easier to attack EMV on the software layer. So as any code is implemented, bugs might arise. Errors might arise. So in essence, the human implementation might make something insecure that was designed to be secure. So if you think of a web app as an example, EMV can be seen as the TLS encryption that is used in that. The server can be seen as either the POS device or the DTV decoder or the ATM or whatever the device is. And the application, well, can be compared to the web app. So when a website is exploited, you don't really see that attackers go and try and attack the TLS. Yeah, you sometimes do, but that's not very, very common. So the attackers usually go for the lower hanging fruit, like attacking the actual application itself. So CSS, XSS, SQL injection, all that. So that's what we also decided to do. So we could see that researchers actually started focusing on this as well. So in 2010, the researchers in Cambridge found a vulnerability that actually allowed them to complete transactions without authentication, so without entering the PIN. They were able to just send back a PIN accepted command, and the terminal would accept it, and they would get their goods or money. So our research as well found system-level flaws in POS devices and mobile POS devices. I'll speak a bit about that a bit later. In 2014, researchers at Cambridge again found a pre-play attack, which was just a poor implementation of that random cryptogram that was said. It was so poor, in fact, that the randomness was just a counter. So yeah. And then in 2016 this year, hackers at DEF CON presented that the actual POS devices were communicating with the backends through an unencrypted channel, which is actually quite bad if you were to be able to intercept that. So we also started focusing our research on that, and at MLUR Labs we have a nice research platform where you publish all our stuff, and yeah, as part of that we decided also to start looking at POS devices and stuff like that. So by looking at the POS terminal, in general, we can see that it has a specific application running on it. So that's usually issued by the bank or the retailer. It has an OS on it, just normal. So it's usually it's an ARM 7, or I think the new ones are even ARM 11. So that's just usually a Unix-based operating system. So, and then you've got the EMV kernel that handles the communications and handles some of the security protocols. And then you've got the physical medium, which you just use it as an entry point. So that's either contactless as the EMV, but the normal POS devices also has USB or Bluetooth, or depending on what terminal you're using and what technology is available. So by actually attacking something through EMV, you would physically need to be able to send the POS device commands. Okay, yes. Okay, yes.
Sorry, that was supposed to be subtle. It wasn't.
So yes, to actually be able to send the device commands, you would need to be able to program something in that would be able to send the EMV command. So for that, we used a Java card. So that's basically just a reprogrammable chip card which you can use to debug or write your own applications on. So the testing process involved us actually taking the card, putting it in the device, recording some data, altering the data, take it out, reading it back into the computer, reading the data, altering the data, analyzing the data, take it out, put it back in the POS machine, take it out, put it in the computer, take it out, put it in the POS machine, take it out, put it in the computer. So yeah, that was, it worked in the end. So we got results from that. So we got the thing to crash, and eventually got a memory corruption vulnerability that led to system level access. And then with this system level access, we actually, being the hackers that we are, we wrote a game for the POS device. So you put your card in, and then it would do the memory corruption vulnerability, and then it would actually program a game in. This one was on a normal chip and pin. It was a normal POS device, and it was called Pin Pad Racer. It was presented by a researcher from us at DEF CON in, I think, 2012. Also, as you see the infection and retrieval cards, we will also be able to infect the devices with malware that during the day, like in the morning you would go, you'd insert your card, you would gather and harvest all the pins and all the magstripe data and all the chip data. At the end, you would take another card, you would retrieve it, and then, hey presto, you have a lot of pins and card data. So the second one that I want to show you is something that we did on mobile POS devices. These are much newer, yet we found a similar memory corruption vulnerability, and we're able to exploit it. Here you can see a Flappy Bird clone called ChippyPin that we wrote. It's quite fun. So that got me wondering to actually, if these vulnerabilities are available on all the interfaces, it should also be available on the contactless interface as well. So moving over to the contactless interface, first off, something that I checked was actually looking at the cards that the NFC cards, the data that it actually has on. So went around the office, got a random batch of cards, everybody that had NFC cards. So what I found was that some of the cards actually displayed ample amounts of data, and other ones were actually quite secure. So this led me to believe that it is actually an implementation fault, not something, it seems to be changeable. So on some cards, yeah, that's actually my card. So just by tap, you can see my last 20 transactions. You can see my track to equivalent magstripe data. You can see my name. You can see the application data from the issuer. You can see the cryptogram that's going to be used. So yeah, quite severe. And that's just by brushing up against me. So something that we saw was that all of the devices that we tested were actually PCI compliant. So yeah, what is PCI compliance actually? It's costly assessments that basically just tells you if a device is functioning as it should be in a certain range of criteria. So what it actually does not do is it does not look at how the device handles unintended input. So all of the devices that we actually found all the vulnerabilities in were PCI compliant. They had the PCI sticker on it, and they were. So yeah, it doesn't really it doesn't really mean that much currently. So yeah, in the future it might mean more, but currently it doesn't mean that much. So to be able to actually test these vulnerabilities, we needed to start fuzzing it. So fuzz testing the protocol and fuzz testing the devices. So fuzz testing is basically the process of supplying the application with large amounts of semi-random data that it would not normally expect. So in order to test the large number of devices, I explained the process previously. So we're tired of actually removing the cards, entering, removing, entering. So we actually built a research platform for the contact stuff. So this was our research platform designed by one of our engineers. So this allowed us to just sniff and alter and fuzz the data and actually manually, automatically insert and actually take out the card for us. So we could just program a bunch of test cases that we wanted and leave it to do its magic. Come back after coffee or lunch, and then we would have a crash or similar results. So having looked at how the previous device works, I really saw it was necessary that we keep up with the technology and actually still look at this new attack surface that the newer past devices gives us. So it's quite fairly unknown. It is still, the communication protocol is still is altered very regularly. So we can see that not a lot of knowledge has gone into this, so then I started extending my research onto this. So why Android? So I decided to look at the contactless, so all of you know that the contactless uses NFC as the technology to communicate. So I looked at either hardware or software attack vectors, and I really wasn't keen to do 6 months of hardware research on this, so I just quickly built an app over the weekend, because we had the full NFC stack already there in Android. So like I said, we rather wanted to do software rather than hardware. It's easier to redistribute as well, and Android actually provides us extra functionality as well, and it is ready available. I mean, anybody in this room, I guess, would actually have an NFC reader on their the phone device, and would be able to use or look at car data if they really wanted to. So this really reduced my research time, not having to delve into the actual hardware side of this. And actually that Android provides a full stack of NFC for us, so it's a full plethora of NFC modes that it actually works with. And in the end, I came up with one device to rule them all, so it was something that can test the cards, can test device, and can proxy communications. So this is to be able to effectively do our research. I developed this contactless research platform to be able to intercept communications between the card and the POS device. Due to the fact that going the hardware route or actually going through the EM side of this actually seemed a bit difficult, and something that would actually waste time rather than add any wealth to this research. So we rather wanted to intercept it via Android communication, the Android platform. So to intercept NFC, this platform would allow you to intercept communications between a card and a device, so meaning you can emulate the device to do whatever you tell it to do, and then send fuzz data to the card. This would also allow you to fuzz a device as if you were a card, so fuzzing the actual device itself and looking at different entry points. And it would also, like I said, allow you to intercept the communications between an actual transaction stream that's going on, just to actually see what's going on between the two devices. So just to give you an example of a normal NFC transaction, firstly, the Android device, we just select the PPSE. This is basically just telling the card that, hey, I'm here, I want to communicate with you. The card would then respond with the application identifier, the AID. This contained all of the applications that were currently on the card, so meaning either the credit card application or the debit card application. The device would then select the application and send the response back. The card would then respond with something called the PDOL, which is the processing options data list, and also the get processing options information. This allowed the device to understand what is further in the card. So the device then initiates an application process, and then the card responds with the goodies, which would be the unwanted stuff, so the track to data or the information or the transaction information. And it also sends the actual file system of the card through, which is the application file locator. So then you can go and start requesting entries out of the application file locator, and then it would give you even more information on the card. So it would respond, and then you can just basically loop until you're done. So yeah, that's basically what this does. So looking at that previous stuff we did, that can be done in about 50 lines of code, getting all of this information. So basically just receiving an intent from the Android application that an NFC device has been detected, and then just responding with all the correct information would give you all of this quite, I wouldn't want my data to be floating around, which it currently is, that specific data. So yeah, it is quite bad. So to look at some of the improvements that I could make, some of the stuff that I've noticed. EMV is quite sensitive to timing. I'm currently busy implementing research done by a security researcher from PwC in Netherlands. He really he looked at the actual proxy side of this before, where he actually caches the data on the one device so that it doesn't have to request the device, make so many requests for the card data from the two devices. So another thing that I actually wanted to do was, having used Burp before, I know what I would like in something that intercepts and caches information. So I'm going to try and make it modular, so add modularity, and so that people can actually add their own code, their own logic and own passes to the data and whatever they want to do to make it fuzz better. And then also just some general performance improvements. So I saw that it lost performance at certain stages during the transaction, and just basically improving that. Something that I also didn't mention was that the actual two Android devices, I found that the best way for them to communicate was over Wi-Fi peer-to-peer. So this was easy to implement. It, like I said, Android gives us the options to do this, and it's quite fast, and it's not fast enough for some of the EMV timings, but like I said, just implement local cache, and I'm going to try and sort that out. So in summary, we can see that there's various NFC standards that exist. We can see that there are various implementations of EMV and NFC, and there's various implementations of where this can actually be used. Another use case that I thought of was maybe actually using this to fuzz card readers for access control, and maybe just seeing if I can't get something like the cool CSI plug over box going that like runs a bunch of numbers and then eventually just opens the door for me. Yeah, so, and the last point that I just saw was that Android actually proves a viable method to proxy NFC comms. And yeah, that's what I got. So